Hello everyone! Today let's talk about something truly powerful, something that comes from deep within our planet and can light up entire cities. I'm talking about uranium. Now, uranium is a special kind of element, a heavy metal that's been around since the Earth was formed. You can find it in rocks all over the world. But what makes it so special isn't that it's just a rock, it's what's happening inside its tiny, tiny atoms. These atoms are packed with an incredible amount of energy just waiting to be released. It's this hidden power that makes uranium the key ingredient for nuclear energy, a way we can generate a huge amount of electricity. So, how do we get from a simple rock to the electricity that powers your video games or your refrigerator? It all starts with the unique properties of the uranium atom. Specifically, we are interested in a certain type of uranium called uranium-235. Think of it as the superstar version of the element. Its atom has a very large and somewhat wobbly center or nucleus. This instability is the secret sauce. When we tap into it correctly, we can start a chain reaction that releases energy in a controlled way. It's a bit like setting up a long line of dominoes. Once you tip the first one, the rest follow, releasing energy as they go. The idea of using atoms for energy might sound like something out of a science fiction movie, but it's very real science that has been developed over many decades. Scientists figured out that if you could split that wobbly uranium nucleus, a process called nuclear fission, it would release a burst of heat. And heat is something we are very good at using. For centuries we have burned things like wood or coal to create heat, boil water to make steam, and use that steam to spin a turbine to generate electricity. Nuclear power does the exact same thing, but instead of a fire we have fission. This makes uranium one of the most energy-dense substances on our entire planet. The amount of energy locked inside a small piece of uranium is millions of times greater than the energy in the same amount of coal or oil. This incredible density is what makes nuclear power plants so effective. They don't need constant shipments of fuel arriving by train or boat every single day. They can run for a very long time on a relatively small amount of uranium, providing a steady and reliable source of power for our homes, schools, and hospitals. It's all thanks to the amazing science of the atom. The journey of uranium begins underground. Miners extract uranium ore, which is basically rock that contains tiny amounts of uranium. This ore is then taken to a special facility called a mill. At the mill, the rock is crushed into a fine powder, and chemicals are used to separate the uranium from the other minerals. The result is a bright yellow powder called yellow cake. It looks a bit like cornmeal, but it's much heavier and, of course, radioactive. This yellow cake is the first major step in turning a simple rock into a high-tech fuel source for a nuclear power plant. It's a concentrated form of uranium, ready for the next stage of its adventure. But the yellow cake isn't ready to be used in a reactor just yet. Remember that superstar atom, uranium-235? Well, in natural uranium, most of it is a different type, uranium-238, which doesn't split as easily. Only about 0.7% of the uranium in yellow cake is the useful U-235, so we need to increase that percentage in a process called enrichment. The yellow cake is converted into a gas, and this gas is spun at incredibly high speeds in machines called centrifuges. The slightly lighter U-235 atoms move toward the center, allowing them to be separated. After enrichment, the uranium has about 3 to 5% U-235, which is perfect for a power plant. Once the uranium is enriched, it's converted back into a solid, a black powder called uranium dioxide. This powder is then pressed into small ceramic pellets. These pellets are tiny, about the size of the tip of your pinky finger. But each one is an energy powerhouse. They are carefully stacked into long metal tubes called fuel rods. These fuel rods are then bundled together to create what's known as a fuel assembly. A single nuclear reactor will contain hundreds of these fuel assemblies, which together make up the reactor's core. This is where all the action is going to happen. Finally, we get to the main event, nuclear fission. Inside the reactor core, we start the chain reaction. A tiny particle called a neutron is fired at a uranium-235 atom. When it hits, the uranium atom splits apart, releasing a tremendous amount of heat, along with more neutrons. These new neutrons then fly off and hit other uranium atoms, causing them to split and so on and so on. This creates a continuous controlled chain reaction that generates an immense and steady amount of heat. This heat is used to boil water, creating high-pressure steam that spins a turbine, which turns a generator to make electricity. Consider this, science in action. Let's talk about efficiency. Think about how much fuel it takes to power things. A car might need a full tank of gasoline to travel a few hundred miles. A traditional power plant might burn thousands of tons of coal every single day just to keep the lights on in a city. Now compare that to nuclear power. Remember that tiny uranium fuel pellet, the one that's about the size of a gummy bear? Well, one of those little pellets contains as much energy as 1,780 pounds of coal, or 149 gallons of oil, or 17,000 cubic feet of natural gas. That is an astonishing amount of power packed into a very small space. This incredible energy density is what makes nuclear power so different from fossil fuels. Because the fuel is so concentrated, a nuclear power plant doesn't need a constant supply chain of fuel trucks or trains. A single large nuclear reactor might only need to refuel once every 18 to 24 months. During refueling, only about 1/3 of the fuel assemblies are replaced. This means the plant can run continuously for very long periods, providing what we call baseload power. That's the steady, reliable electricity that is always on, day and night, regardless of whether the sun is shining or the wind is blowing. Let's put some numbers on it to really see the difference. To generate 1 gigawatt-hour of electricity, which is enough to power about 750,000 homes for an hour, a coal plant would need to burn about 315 tons of coal. An oil-fired plant would need about 6,000 barrels of oil. A natural gas plant would need about 3.2 million cubic feet of gas. A nuclear power plant, on the other hand, would use just a few pounds of uranium. This efficiency has a huge impact not just on logistics and transportation, but also on the amount of land needed for mining and the overall environmental footprint of the fuel extraction process. This efficiency also means that nuclear power plants have a very high capacity factor. The capacity factor is a measure of how often a power plant is running at its maximum output. A typical nuclear power plant in the United States, for example, has a capacity factor of over 92%. This is the highest of any energy source. For comparison, solar power plants have a capacity factor of around 25%, and wind farms are around 35%. Because they can only generate electricity when the sun is out or the wind is blowing, nuclear power's reliability and efficiency make it a powerful tool for building a stable energy grid. So, how much of our world is actually powered by the atom? Well, as of today, in mid-2025, nuclear power is a significant part of the global energy mix. There are about 440 nuclear reactors operating in over 30 countries around the world. Together, they generate about 10% of the world's total electricity. That might not sound like a huge number, but honestly, it's a massive amount of power that is produced without releasing the greenhouse gases that cause climate change. For many countries, nuclear energy is not just an option, it's a cornerstone of their entire energy strategy, providing them with energy independence and a stable power supply. Some countries rely very heavily on nuclear power. The champion of nuclear energy is France. An incredible 70% of all the electricity used in France comes from its fleet of nuclear reactors. This has made France one of the world's largest net exporters of electricity, and has given it some of the cleanest air in Europe. Other countries that are big on nuclear include Slovakia, Ukraine, and Hungary, all of which get more than half of their electricity from nuclear fission. These nations have embraced the technology as a way to ensure they have a reliable power source that isn't dependent on importing fossil fuels from other places. The United States is another major player, even though nuclear power only makes up about 19% of its electricity. Because the US is such a large country, and uses so much energy, it actually has the most nuclear reactors in the world, and generates more nuclear electricity than any other nation. On the other side of the globe, countries in Asia are rapidly expanding their nuclear programs. China, for instance, is currently building more new nuclear reactors than any other country, as it looks for ways to power its massive economy while reducing its heavy reliance on coal and cutting down on air pollution in its major cities. The global use of nuclear power is always changing. Some countries, after the Fukushima incident in Japan in 2011, decided to phase out their nuclear plants. Germany is a key example of this. However, many other nations are either extending the lives of their existing reactors or are planning to build new ones. There's a growing recognition that as the world tries to move away from fossil fuels to fight climate change, nuclear power offers a powerful, carbon-free option that can work 24/7. So the global conversation about nuclear power is very much alive and well. One of the biggest benefits of nuclear power, and a major reason we're talking about it so much today, is its impact on our environment, or rather, its lack of impact on our climate. Nuclear power plants do not burn anything, so they do not produce carbon dioxide, the main greenhouse gas responsible for global warming. Generating electricity with nuclear power is clean from a carbon perspective. In fact, a switch from a coal plant to a nuclear plant can prevent millions of tons of carbon dioxide from entering the atmosphere every year. This makes nuclear a powerful ally in the global fight against climate change. However, nuclear power comes with its own set of very serious challenges that we must manage responsibly. The first is nuclear waste. The used fuel rods from a reactor are highly radioactive and will remain dangerous for thousands of years. Right now, most countries store this used fuel on-site at the power plants in specially designed pools of water or in large dry concrete casks. The long-term plan for most countries is to bury the waste deep underground in stable geological formations, but finding and building these permanent repositories has proven to be very difficult, both technically and politically. The other major concern is safety. While modern nuclear reactors have multiple layers of safety systems and are built to withstand extreme events, accidents can happen, and when they do, the consequences can be severe. The accidents at Chernobyl in 1986 and Fukushima in 2011 are powerful reminders of the potential dangers. These events have understandably made many people nervous about nuclear power and have led to extremely strict safety regulations around the world. Ensuring the safe operation of these plants is the #1 priority for the entire nuclear industry. So, what does the future hold? Scientists and engineers are working on new types of reactors that could be even safer and more efficient. These are often called advanced reactors or small modular reactors or SMRs. SMRs are designed to be built in factories and transported to a site, making them cheaper and faster to construct. Many of these new designs have passive safety features, meaning they can shut down automatically without human intervention in an emergency. Some future designs might even be able to use the nuclear waste we have now as fuel. The journey of the atom is far from over. As we look for ways to power our future cleanly and reliably, uranium and nuclear energy will surely remain a big part of the conversation.